We cannot hear you, not see you. Okay, now we can see you. So welcome, and I'll leave you the word.
Okay. So should I start?
Yes, please.
Okay. Hello everyone. I am MD Rajiv Hossen from UT Arlington. I will present our work titled Mobile Task Offloading Under Unreliable Edge Performance. This is a joint work with my PhD supervisor Muhammad Islam from UT Arlington. This is a paper on mobile edge computing. We will see how unreliable edge performance can affect offloading performances and how to take informed offloading decisions. Nowadays, mobile devices are not limited to taking phone, sending in message, using social media, etc. It enables us to play high resolution games, use augmented reality, use face recognition, do heavy computation. However, due to space limitation, mobile devices are equipped with small batteries and very low computation capability. To rescue from this, we can offload some tasks, some applications to the cloud. But cloud is a centralized setup and it is in long distance. So it takes a lot of time to complete a task. So the computation came closer to the end devices, that is at the edge of the network. As computation is done closer to the end devices, it gives us several advantages. It saves a lot of energy from the mobile device. It incurs less latency than traditional cloud computing. However, if an application is data intensive rather than computation intensive, it may incur delay and consume an additional energy for data transmission. So we need to decide when and for which task to offload. Several work has been done in mobile edge offloading area. Many authors proposed solution to optimize latency and energy for offloaded tasks. Moreover, they also considered several combination like single device, multiple device, single edge server, multiple edge server. However, all of this work assume the offloaded task will be always processed at the edge. This may not true always due to the increasing use of renewable energy in computation. The intermittent nature of the renewable energy can throttle edge capacity. So this can make edge unreliable from time to time. Also, the user request may not follow a pattern. The load can vary rapidly and it can reach to a peak and also it can reach to underutilized. As a result of the situation, edge may further offload to the cloud. For example, the mobile device offloaded to the edge. But due to the low power or high utilization, the edge will further offload it to the cloud. And the same issue then as again, and then edge return to the mobile in very slower than originally offloaded to the cloud. A mobile device does not have any idea what is going on in the edge and the cloud, and it wait long time than anticipated. To solve those issues, we proposed a solution that will optimize battery uses in mobile devices and improve task completion time, just like basic mobile edge offloading requirement. However, we also consider the unreliability of the edge server. We used learning to navigate in this unknown environment. We formulated the problem mathematically and form an optimization problem that will optimize task completion time and energy for all users. We want to minimize the cost of this equation. This is the optimization equation where the TK is the task completion time, W is the EK is the energy consumption, W is the weight variable or weight parameter, and X is the decision variable. And why we need to combine the minimize the cost of this. And W, the weight parameter is important. It helps us to emphasize on energy or task completion time. We can solve this optimization problem like traditionally. However, there are some issues that need to be resolved or I need to discuss before we go to the solution. First of all, the offloading decisions are tied together. For example, I have some task and I in near future I may need a task. There may come a task that will need the battery most, or I can use the battery currently as much as I can. So the task decision are tied together, and I need to be aware of this future situation. Moreover, the task completion time and the energy are very hard to estimate due to the fact that the edge will further offload to the cloud. So from the mobile device, will not know what will be their final value unless I get the uploaded task returned from the edge. Also, they are very hard to generalize because of the underlying architecture. The mobile device can vary in architecture, the edge server can vary in architecture, so they may use battery differently. And lastly, the different area may have different resource requirement. So for these issues, there is no one solution fits all. Traditionally we cannot solve this and adapt to the situation, so we need some kind of learning that will helps us to understand the underlying environment and work with the solution properly, optimally. As a result, we use MDP with reinforcement learning. This is a basic reinforcement learning algorithm. The agent take an action based on the state variable and from the environment. Then based on the action taken, it get rewarded and it get to the next goes to the next step. Based on the reward can be positive or it can be negative. Based on the reward, the agent over time the agent learn which action to take based on its state variable. And to do this, it doesn't need any previous knowledge like supervised learning or unsupervised learning. There are several reinforcement learning algorithms, like Q learning, deep Q network, deep deterministic policy gradient. These algorithms are used for different environment setting, like for continuous variable, for finite state space, for continuous state space, etc. This is the Markov decision process, the basic of reinforcement learning for our problem. Here, the system state consists of a variable task, which includes data size and CPU cycle. It also includes available energy. It includes the mu m mobile computing capability, mu e the edge computing capability, and the uplink rate. The action consists of two variables like xk that can be 0 for local processing or 1 for edge processing, and a reward from state xk with an action to the next state. We give the computation cost as a negative reward to optimize it. So this problem, this Markov decision problem, we can solve it using Q learning. However, the Q learning becomes very poor and it performs poorly when the state space becomes very large. Moreover, the available energy here is continuous variable. So the Q table, it grows larger and larger, and at one point it becomes unmanageable. So we used DQN to solve this issue. And another thing is the reinforcement learning problem assume the environment is Markovian. The Markovian means the next state depends only on the current state. However, the next user request may not depend on the current user request. So this does not follow Markov property. So we solved this using LSTM long short-term memory to estimate user request and state transition. This is the network architecture for our solution. The input is state, and then we use fully connected layer and LSTM layer, and the output are Q values. Based on the Q values, we take input and with the highest Q values. We did experiment based on synthetic and real data. The edge uncertainty was simulated using Uber request data. The edge to cloud latency was added using ping test to several AWS regions. And these are the settings for synthetic workload. We use data sizes with 500 kilobyte to 1 megabyte randomly distributed, CPU cycle with 500 million to 2000 million randomly distributed, and in 1.5 gigahertz processor, it take with the minimum it take 0.33 second. And we used for the simulation purpose, we use battery capacity of 120 joule and transmission power 500 milliwatt. The mobile capacity 1.5 gigahertz, it varied from 20 to 100%, like 20%, 40%, 60%. And the cloud is 3.6 gigahertz, and it was fixed, and the edge was variable with the simulation, like with the trace. We compared our algorithm with 4 different algorithms, like all mobile. So all mobile is all the tasks was processed in the mobile device. All edges, all the tasks are offloaded and processed in the edge. And greedy is oblivious of the edge server further offloading to cloud and optimized for each task independently. Moreover, it does not consider battery level. However, when the battery level goes below 20%, we restrict local processing. And when the edge capacity went further more than 75%, we restrict edge processing. We present our work with a box whisker plot. Here is a little change, like this bar and this high bar represent 10 percentile and 90 percentile, and the box and lower box and upper box represent 25 percentile and 75 percentile, and this is the median. So our algorithm deep2 we compared with all mobile, all edge, greedy, and optimum. From this figure, the task completion time, all mobile performed worst among all algorithms due to its limited capability. All is, and this is the mean. So we can see that the mean is greater than all of this, and all edge perform better than all mobile. Greedy perform better than all mobile and all edge, but it perform worse than all optimum and deep2. It perform better than all mobile and all edge because it can choose local or edge based on the variables. However, as it perform worse than these two algorithms because it's inaccurate estimation of task completion time. In case of energy, all mobile, all edge perform best because it just need some small transmission energy, and obviously all mobile perform worse. We also did an experiment to see the impact of offloading from edge. We varied the offloading percentage from 10% to 50%, and we see how it changes. Now, for this task completion time, we see that our approach deep2 can maintain performance with optimum. As the percentage goes, it can maintain percentage, maintain its performance. But greedy, on the other hand, drift further away from the optimum because it is oblivious of these percentage changes, and it inaccurately estimate. In case of energy consumption, greedy perform constantly because its offloading policy doesn't change with edge to cloud percentage. As a result, this doesn't incur additional energy. After passing this 40% bar, the deep our approach and optimum perform worse than the greedy because they start processing in mobile device then in large number than edge device. Other than this, we also evaluated our algorithm to with two different simulation and with various different simulation and parameters. There are some limitation in our work, and in future we will solve this. First of all, the training time. It takes a lot of time to train our model. So we in future we may use federated learning or we may use the pre-trained model to faster this training process. We will also use the real world mobile user data instead of simulated data or synthetic data. Thank you very much. Questions, please.
Thanks, Rajiv. Are there questions?
Yes, I have a question. So thanks again for the presentation. My question is related to, say, the future work you are planning to. What could be the scenario you will apply your framework? So which kind of data are you planning to analyze? I see here that you have real-world mobile user data. So to which kind of data you could apply your methodology?
Okay, here you can see we use the data sizes randomly distributed, the CPU cycle randomly distributed, and battery capacity. So we from the existing literature we found this data. We found this literature and uses this. But it would be better if we can actually see the like face recognition in mobile application and set up a server like edge server and actually offload from mobile to edge and see how it changes. So if we can use the if we find existing data, that would be better, or we can use we can generate our own data.
Okay, so for which kind of problem you can then address in the future?
Mostly the compute like face recognition or live video streaming, this kind of application.
Okay, thank you.
Thanks. Other questions for Rajiv?
Thank you.
So if there are no questions, we'll thank you again, Rajiv. And